talking about. We're really embarking on sort of a new phase of exploration. And when I say we, I don't just mean NASA, I mean actually the world, because the program I'm going to be talking about, the path that I'm going to be describing tonight, is not just a path that's being worked on by NASA, it's actually being worked on by all of the space agencies of the world. There's a group that's worked on something called the Global Exploration Roadmap, on how can we, as all of the nations of the world, work together to take on a huge challenge, which is moving humans beyond low Earth orbit. No one country, no one nation can certainly afford to do this on our own, so what is the best path forward? And all the nations of the world are actually working very closely together on this. So I'm going to be talking to you today about NASA's part in that, what we're working on, what our goals and objectives are, at least in the near term. Like all space agencies of the world, we're trying to do something very bold over quite a long time period, and that's a challenging thing to do in a world that usually doesn't work on 5, 10, 15, 20-year time horizons. Most governments work on much shorter time horizons. So to lay forward a framework that builds piecemeal to accomplish something very big is a huge challenge. And that's, again, why it's so important that this be not a US effort, but a truly international effort. I'm going to start by taking a step back and talking about how this fits overall, what's the science rationale. Then Jim was going to talk about the technologies and some of the first steps that we're working on, and I'm going to muddle my way through his slides. The science slides were obviously my slides. So at NASA, the science we do, as you probably well know, literally spans the universe, from the science that we do studying our own sun, not just from a point of view of trying to understand how a star operates, how a star evolves, but from the fact that, as most of you probably know, the sun produces huge streams of particles in solar flares and coronal mass ejections that can disrupt communications around the Earth. And obviously none of us want anyone's cell phone coverage to be interrupted for even a moment, because that would be a crisis. So trying to understand the behavior of the sun, but especially then as we look forward to eventually sending humans beyond low Earth orbit, beyond the protection of the Van Allen radiation belts, where they're going to be subjected to much more bombardment by particles. So trying to understand the behavior of the sun, using our network of international assets that are right now studying the sun and the ones we hope to put into place over the next several years to really get at more, how does this star operate, and how can we better understand and predict its behavior and how it affects us. The work that we do in astrophysics, I think, is some of the stuff that sometimes makes your brain hurt, like when you try to understand gravitational waves and the implications of that for the Big Bang. But a lot of the images that have been returned by assets like Hubble, I think look more like art than science. The stellar nurseries that we've imaged, the deep fields of galaxies that were obviously forming at much earlier time periods than we'd anticipated in the history of the universe. The multitude of things that we've been able to learn about the very early stages of the formation of the universe, the formation of galaxies, has been quite dramatic. The International Space Station is another example of where we do a huge broad range of science every day, from trying to understand the effects of deep space on the human body, which I'm going to come back to in detail later in the talk, to some of the fundamental physics that we plan on doing. In a couple of years, we're going to be launching a cold atom lab that will take atoms down to near absolute zero to better understand complex atomic behavior, to the work that we're doing in all kinds of genetics. For example, the fact that some bacteria, when you send them into space, like salmonella, become more virulent. Other types of bacteria become less virulent in space. So we're doing an awful lot of genetics research on things that range from plants to fruit flies. We're sending our first bunch of rodents up later in the summer to do an extensive amount of basically genetics, omics type research to understand what are the effects of these different systems that zero gravity is having. And we know, again, in all kinds of different, either from plants to fruit flies to humans, When you take gravity out of the equation, genes start turning on and off and doing weird things. And so trying to use that information to then better understand group behavior is something that we're able to do every day up on the International Space Station. Our studies of the solar system, we literally right now have spacecraft going from one end of the solar system to the other. We have the MESSENGER spacecraft around Mercury that's been returning all kinds of interesting information about the evolution of that planet's surface, to the New Horizons spacecraft that we have on its way to Pluto, to the Juno spacecraft on its way to Jupiter. So very extensive programs in trying to understand the bodies of our own solar system, how have they evolved, and how can we use that information to better understand our own planet. To the 17 satellites that we have in orbit around the Earth right now that are measuring basically every aspect of our water cycle. We have a satellite launching this summer to study atmospheric carbon. We have satellites that look at the gravity map of the Earth that we can use to see when aquifers are being drained of water. We have a global precipitation measurement mission that's part of a multi-nation core of measurements that are allowing us to measure precipitation globally around the planet every 3 hours. All aspects of climate and weather are being addressed by our fleet, as well as the international fleet of Earth-observing satellites. So if you look at this, it's quite a breadth of science. And so the question becomes, what's the connection? And that's my job as sort of chief scientist at NASA, is to look across all of the different science we do and say, you know, what are the connections? And what does this have to do with going to Mars? And most of our guiding documents, and at NASA we use a series of guiding documents called decadal surveys, where our National Academy of Sciences in the US through the National Research Council every decade organizes astronomers, planetary scientists, earth scientists, and microgravity scientists, and they put forward a 10-year plan that really comes bottom up from the scientific community. And we use those decadal surveys as the guiding documents to lay out the kind of science that we do. And in a lot of those documents, as well as our kind of fundamental strategic plans of NASA, you find some variation of these three really simple questions. Are we alone? How did we get here? And how does our universe work? And so whether you apply these questions to the universe and say, what are the origins of the universe? What is the evolution of the universe? If you apply it to planetary science and say, how did we get this diversity of planets that we have in our solar system? And how can we use that information to better understand the state and fate of the Earth? It's really these fundamental questions getting at what are the origins of the planets, the universe, and the stars, and how can we understand how they change over time. And when it comes to the universe, being able to have assets that can look deeper and deeper into space, and thus deeper and deeper into time, we can get at, again, some of these fundamental processes that shape the universe. Obviously, the search for dark matter is ongoing. We have an instrument up on the International Space Station that's looking for my favorite acronym in science, WIMPs, Weakly Interacting Massive Particles, to the work that we are going to be able to do with the James Webb Space Telescope, which will launch in 2018. A really key mission for NASA. It will again look deeper into space, deeper into time. It will be able to better understand, study stellar evolution. It will be addressing black holes at the centers of galaxies. But for me, as a planetary scientist, even more intriguingly, Hubble will be able to, or the James Webb Space Telescope will be able to look at the atmospheres of planets around other stars. Extremely interesting asset that will launch in 2018. So these questions about the universe and the data that we're increasingly capable of being able to collect is tremendously exciting. And again, this isn't a US thing. All of these missions are international efforts. When you look at our own solar system, you know, I talk a lot with kids groups. I talked to some kids at Imperial College this afternoon. And I like to tell them, you know, when I was growing up, we had 9 planets. You guys only had 8. And obviously we used to have poor Pluto here at the end, but it's gone now. But, you know, back when I was in school, in all seriousness, you know, we had ideas, okay, this is what a solar system looks like. You have rocky planets close to a star, you have gas giants further out from the star. And we had a model that said, well, you know, it's temperature and pressure gradient away from a parent star, and that's why we have what we have. Well, of course, when you only have one thing to study, you can develop a great model to explain it. But once you start getting more data, you have to start revising your theory. And over the last 20 years, amazingly, that's what we've been able to do, because increasingly we've developed the technology to be able to detect planets around other stars. So we went from having 8 or 9 planets to study to, in the 90s, all of a sudden finding planets on almost a daily basis. And of course, early on we had the technology to detect Jupiter-sized planets. And we started finding them really close to their parent star, or far from their parent star, or all different distances. And we realized that that sort of more simplistic model that we had to be adjusted. And we now have something called the NICE model, developed in Nice, France. On the other hand, you know, fasten your seatbelt, because what's happened over the last several years is a new telescope that was in operation. It lost one of its reaction wheels, so it's now in a transition stage. The Kepler Space Telescope, which is responsible for all of these yellow dots, over 3,500 candidate planets that we've discovered in the last several years. And this chart is just showing you their size and their distance from their parent star. But what's exciting is, you know, early on I was saying most of the planets we were finding were these Jupiter-sized planets, which again we found sort of close in or far out. Kepler gave us the technology to start detecting planets in the size range of the Earth. And sure enough, it's found that planets between the size of Earth and Neptune are actually quite common. So this is incredibly exciting. We now have this population of candidate planets that we can turn the James Webb Space Telescope to start trying to determine what the atmospheres of these extrasolar planets could be. Incredibly exciting time, because my guess is, just like when we had the study of one solar system, we now have been studying atmospheres of planets in one solar system. When we have the ability to start studying atmospheres of hundreds of planets, my guess is a lot of what we think about how planets evolve, how their atmospheres evolve, is going to be turned on its end. So to me, when you see new data like this, that again, brand new, coming in over the last few years, it's really going to turn science on its end. And I think it's an incredibly exciting time in this study of extrasolar planets, really the whole birth of a science and its implications for our own solar system, our own planetary evolution, I think are tremendously exciting. What links extrasolar planets back, believe it or not, to why we want to go to Mars is this fundamental question that I had on the slide in the beginning. Are we alone, and how did we get here? Has life evolved on any other body? Okay, based on what we know about life on Earth, which you can say right from the beginning, are you sure we should use that one model as the be-all and end-all model? No, but it's the one we have, so let's start there. To get life on Earth, we think you need 3 basic things. You need a source of organics. That's not very hard, because comets and asteroids have delivered those materials all over our own solar system. So we think those things are pretty common. You need a source of energy. Maybe not that hard either, because lots of planets have volcanoes, some planets have lightning. So sources of energy are maybe not so hard either. What we think is the hard part is having liquid water. So when we look in our own solar system and say, where did we have liquid water persistent? Mars certainly instantly comes up as a huge candidate, and I'll talk more about Mars in a minute. But Mars isn't actually the only part of that story. Europa, Jupiter's moon Europa, it has a water ocean under this icy crust, which we think is in some places maybe thick, and in other places very thin. And just in last December, with the Hubble Space Telescope, we actually, a scientist discovered that there were plumes of water coming out of the south polar region of Europa. Now, what would that be? Well, this is Enceladus, one of the moons of Saturn, and you see these plumes coming out of Enceladus. Those are actually geysers erupting from Enceladus, and we've actually flown the Cassini spacecraft through those water plumes. That's how, partially, we know they're water. And not only did Cassini measure water in those geysers, it also measured that there were some kind of organic particles in them. The mass spectrometer on Cassini It doesn't go out to heavy enough mass number for us to be able to really identify what those organics are. But we know they're there, and we know it's interesting. So we know, okay, here are two other destinations in our own solar system besides Mars, Enceladus and Europa, that both have these water geysers, that both probably have organics, and therefore have the potential for life. Europa is particularly interesting because most of you have heard of black smokers, those volcanic pipes on the ocean floor that are extremely rich biological environments. Well, some of you might be familiar with Jupiter's moon Io. It's the really volcanic moon, volcanoes all over it. And the reason it's volcanic is because that huge mass of Jupiter is constantly pulling on Io. Huge amount of friction, melts the interior, produces lots of volcanoes on Io. Well, Enceladus or Europa is not that much further away from Jupiter. So think about underneath this icy ocean, an icy crust, the ocean, there's got to be, it is highly likely, scientifically based on what we see on Io, Europa's distance, that you probably have volcanic activity at the base of that European subsurface ocean. Again, these ingredients that we think are so intriguing. So we know that we have these huge questions about life. We know we would like to understand our own solar system better as a framework for going out beyond our own solar system as we begin to study planets around other stars. And we certainly have these targets. So we've focused on Mars because it's a place where humans could go. It's a place where humans could live. And we know that surface water existed for long periods of time. And then we have our more exotic targets that we would eventually like to visit. But if we're trying to move off of the Earth, you have to do it in a stepwise fashion, because as I'll get into in a little bit, the challenges are clearly great. And near our own system, obviously the moon provides an easy and very interesting place to study. The moon is often referred to as a witness plate for the Earth. All of those craters on the moon preserve the heavy bombardment that the Earth was subjected to very early in its history. So being able to better understand that cratering rate, those processes that took place on the moon actually give us insights onto the Earth. So studying the moon is actually incredibly important for understanding the history of the Earth. Other potential targets for exploration are the building blocks in our solar system. And comets and asteroids certainly fall into that category, with comets being obviously a really interesting source of organics and volatiles for planets, and asteroids as well, being a source of both volatiles and the building block materials of which all the planets are made. So an asteroid presents itself as an interesting potential target. Not to mention that asteroids and the Earth obviously have a long-term interacting history that we would like to better understand in terms of what are the population of near-Earth crossing asteroids that could potentially impact the Earth. But Mars really remains our prime focus. Why? Why don't we just go to the moon? Why do we want to go to Mars? And to me, again, it gets back to this question of life. And as a geologist, I'm a field geologist, I like to go out and bang rocks with a hammer. And the ability to send a human down on the surface to do science, I think, is the way we're ever going to significantly be able to prove that life evolved on Mars and what the nature of it is. You're actually going to need scientists down on the surface of Mars doing work. And again, it's because of this rich history that Mars has had with long periods of water viable on the surface. We've landed now successfully on Mars over 7 times, with the most recent being the Curiosity lander in Gale Crater. And again, Curiosity has been able to demonstrate that the surface of Mars did have these sustaining environments for life that were not too acidic, not too basic, where again we feel that water was stable on the surface for long periods of time, enough to form the kind of minerals that you would need, or that demonstrate that water was stable. From all of these landing sites, all of these places we've been able to go on Mars, We've been able to put together this scientific story, but one of these, I think it's this one, is actually the Viking landing site that was stable. The rest of these all came from our rovers. And you think, well, why send humans? Why don't we just have rovers? Most of these rovers, well, Pathfinder, the first rover, basically only went meters. Spirit and Opportunity went much further, partially because they lasted a lot longer than we thought they would, with Opportunity still operating now for over 10 years. But even with Curiosity, you're limited by how far we can go and how fast we can go, just by technology. We're talking sort of couple kilometers in a week. Just think if you had a human on the surface. You could assess 3 or 4 outcrops in an hour, not in days, not in weeks. So the slowness of the science, the ability to react and interact, which to a geologist is something that we do in the field on a normal basis, is something that I feel is necessary to really truly understand Mars. So as an international community, what have we been doing at Mars? So, because saying, oh, we want to go to Mars as humans, we're already at Mars. We've just been sending our robotic workers there. And all of our missions have followed a theme of trying to understand what are the habitable environments. So where's the water? How can we use that water to demonstrate that you have long-term habitable environments? And then as our instruments get more sophisticated, our rovers get more sophisticated, actually seeking signs of life. Can we find evidence of organics on the surface? And so again, a very international program from instruments, like you mentioned, I'm on the ESA's Mars Express mission, to our several orbiters. We have the MAVEN mission, which is going to go into orbit around Mars in late September, early October. That's going to be studying the atmosphere of Mars. To ESA's Trace Gas Orbiter, which will be launched in 2016, also studying the atmosphere of Mars. Our international mission InSight, which will be looking at the interior structure of Mars. The interior structure is important for, again, understanding this long-term history of water on the planet. To the ESA ExoMars rover, to NASA's Mars 2020 rover. So we are exploring Mars. We are already there. We're doing it internationally, and we're also actually collecting data already to get us ready to send humans to Mars. The Curiosity rover was instrumented with instruments to really characterize its entry, descent, and landing in terms of collecting data that would be useful to a future manned mission. It carried a radiation instrument to characterize the deep space radiation between Earth and Mars, and then to characterize the radiation environment that humans would be subjected to on the surface of Mars. And likewise, the Mars 2020 rover will carry both those sorts of instrumentation, and potentially something that will begin to take us down the path to in situ resource utilization. And again, the ultimate goal on this, to me, is, and John Grunsfeld, who's actually the head of the science division at NASA, he likes to say, you know, we're not sending astronauts to Mars, we're sending scientists to Mars. Because it's really those scientists, those technologists that we want to get down on the surface, because we're not going there for the fun of it, we're going there to work and to do science and to explore. So, how are we going to go about doing this? And right now, we've developed something that we call the Road to Mars, trying to formulate a defensible path that's also flexible, that as you learn, you can figure out what the next step is. Because the problem is, as we go through, there are huge technological challenges in this, so we're going to have to be adaptive and sort of learn as we go. So the phase we're in right now is sort of a two-part phase, where we are, first of all, we're Earth reliant. So we're doing extensive research, again, on the International Space Station, to try to understand the long-term effects of space on the human body. A lot of research to be done. Microgravity environment affects basically every human system, from the cardiovascular system. It increases intracranial pressure, which has led to vision problems. Muscle wasting, bone density loss, lots of effects on the human system in microgravity, which to me is also just fascinating from a scientific point of view. If you say, you know, as humans we evolved in this 1G environment, and you take us out of it and we actually don't work so well. And okay, how can you then turn that information around and maybe use it for medical advances here on this planet. So we have a huge amount of scientific work to be done in this Earth-reliant mode to get ready to send humans to Mars. Then we'll be ready to move on to something we call the proving ground. Can you go out into the near-lunar environment and start demonstrating the technologies, the capabilities that you need in a place that's 1 or 2 days away from the Earth? So can we do it at a safe distance from the Earth, that things go wrong, and you're not in an irretrievable situation where you're 3.5 months on a 7-month journey to Mars? So using this proving ground, using this near-Earth space to start moving beyond low Earth orbit is the sensible thing to do. And then obviously in the interim, while we're doing this with humans, there's the work that we're already doing with Mars. The science I talked about that we're collecting with missions like MAVEN, with Curiosity, that we'll be collecting with all of our international Mars assets, to do the science that we need to close what we call the strategic knowledge gaps. Things like, what is the characteristic of the dust on Mars? For example, when the Apollo astronauts were coming back from the moon, they got back into the capsule, and all the dust that was on their suits, when they got into zero gravity, it started floating around the capsule, and they were inhaling it. It was getting into all the systems in the Apollo capsule. Dust is something that you really need to worry about, not just from a human health point of view, but from a, is it going to get into your mechanical systems and break them point of view. So scientifically understanding, we know Mars is a very dusty place. What are the characteristics of that dust? How is it going to behave? Incredibly important. Characterizing the Martian atmosphere. Mars has a very thin atmosphere, but it's actually quite variable. It takes about 7.5 minutes to get from the top of Mars' atmosphere to the surface. There's a great video that, if you haven't seen it, that they put forward, JPL put forward for the Curiosity landing, called 7.5 Minutes of Terror, where they explain how difficult it is to get large amounts of mass down onto the surface of Mars. Okay, now we're talking about something 10, 20, 50 times more massive than Curiosity. Huge challenge. We have science to do to get ready for that point. So I would argue that all future Mars missions that the US will be doing will now be joint human exploration science missions. We'll be doing great science that we need to do at Mars to answer some of our fundamental questions about Mars, but we will also be testing technologies, making scientific measurements to help us get ready for sending humans to Mars. So more specifically, what are we actually doing on the International Space Station? I talked a little bit about the human health and human performance issues, and it doesn't just go to, again, human health, which has all these effects, but it's how do we develop and test nutritional food systems that will keep astronauts healthy for the 7 months to Mars, when we can't resupply with fresh fruit and vegetables like we're able to do with the International Space Station right now. How do you feed people food that is not only appealing, so that they don't get even more bummed out than they already are about being trapped in this little capsule with 3 of their maybe not so best friends, but how do you keep them eating in a way that's nutritional and helps offset potentially some of these other effects. And as an aside, I have to tell you, it's been, of course, personally disappointing to find out that one of the ways they've been able to offset some of these issues, like bone density loss and muscle wasting in astronauts, and even some of the intracranial pressure. Don't eat too much salt, eat lots of fish, eat fruits and vegetables, and get lots of regular exercise. So it's the same prescription everywhere, right? You know, do the right things and you'll stay healthy. It's the same on the International Space Station. But that's not the only thing we're doing. We're also dealing with issues like using the ISS as a technology testbed for some of these technologies that we're going to need. One of the huge ones is closed-loop life support. Life support systems, making sure that the CO2 levels don't get too high, that the oxygen is at the right levels, is a huge challenge. Water supplies. We're already very successfully in the last year or so now recycling urine. That's one of the main sources of water now on the International Space Station. So some of these systems that we've developed up there we can use, but can we translate those into systems that, for example, might be compact enough to be used on a 7-month mission to Mars? So huge issues with life support, things like docking systems, just logistics and maintenance, human health, how do you predict what medical emergencies might occur, how can we start training and developing procedures for long-term human health in space. And certainly our commercial crew and cargo programs are a huge point from NASA's point of view in taking us to a position where NASA's not utilizing most of its resources in maintaining a presence in low Earth orbit and transporting humans back and forth in low Earth orbit. That's turned over to the commercial sector, and NASA can focus its assets on the next steps to go to Mars. I've mentioned time and time again this human health issue, which I think is fascinating, and radiation is clearly one of the biggest challenges that we face. And even worse, radiation exacerbates that bone density loss problem. So it's not only potential radiation effects on increasing people's cancer risk, increasing potential cognitive issues, but it also then even affects your bones. So trying to find ways to potentially shield, obviously you can't use metal because it turns out the cosmic rays coming in would just energize whatever metals you would be trying to shield with. People are talking a lot about water. Can you use a water layer around a transport vehicle as maybe the best way to provide shielding? Do you only need to shield part of it? Can you have an escape place where people could go if they knew there was a major solar event? So huge issues on how do we protect humans from radiation on this long duration trip. And again, we're doing a lot of work on that, as well as work on, for example, teaching the astronauts to do diagnostics with a sonogram machine, thinking about, again, how do you send people out so that they are no longer in an Earth-reliant position. And that's why working in that proving ground of near the moon, being able to test out a lot of these technologies and procedures when you have a safety valve of coming back to Earth is so important. So really the exploration of Mars has three separate parts to it. It has just the pure human exploration aspects, and this also follows how we organize ourselves. It has the science aspects that I've been talking about, as well as technology development. So it really takes three areas of NASA that over history have actually been separate areas and has us working together. And that's really exciting to be able to move into a mode where you say, okay, these programs really aren't separate. We may be in separate areas, but we're all working towards a common goal. And there's a huge amount of really fun and exciting overlap. Now, our first step that we've outlined in this path to Mars is a mission that's called the Asteroid Redirect mission, where we would go, we're looking at two different scenarios right now for the Asteroid Redirect mission. One is to go and capture a small asteroid robotically and bring it back to that near-moon space and put it in a lunar orbit. The other option is to go to a larger asteroid and grab a boulder off of it and bring the boulder back. And so we're still studying those two different options. Then once the boulder was in the cislunar space area, we would send humans, in a vehicle that would also go into a similar orbit to actually go and collect samples and test different technologies and capabilities in that space, giving them something to do while, again, testing out these great technologies. There's three different parts, actually, to this program that we're working on. And the first is really the strong science part, and that's the identification part. As I briefly mentioned, asteroids aren't only interesting because they are the building blocks of all the planets. They're also interesting because every once in a while they hit us. And that doesn't happen overly frequently, but when it does happen, it's obviously very dramatic. Even when you saw something very small, like the Chelyabinsk event that we had a few years ago that was, again, very dramatic, luckily not very harmful, to larger craters like the Cretaceous Tertiary Boundary event that had huge effects on the Earth's system. So the interaction of asteroids and comets with the Earth is something that we would like to better understand. And so our first part of this is actually just a huge identification program. We're doing that utilizing the public utilizing our network of telescopes that we have as an international community all around the world. We've reactivated a spacecraft that we had called WISE. It's now a new mission called NEO-WISE that's actively searching for new asteroids. So what we'd like to do is to get a really strong characterization of the near-Earth population of asteroids that are potentially Earth-crossing from a scientific point of view, from a planetary protection point of view, just to better understand that population down to a smaller level than we've had before. So there's a lot of good science that's going to come out of that in the next couple of years. The next part of the mission is this redirect phase, where we would send this robotic mission out to capture an asteroid. You think, well, why do that? Well, one of the best technologies that we're going to be testing with that is electric propulsion, the ion propulsion unit. The ion propulsion unit gives you a lot of thrust, but slowly. So it's not good if you want to get somewhere fast, but what it would be extremely useful and very needed for would be taking large amounts of cargo to Mars that you would need. So before you ever sent humans to Mars, you would send all kinds of infrastructure there to be waiting for them when they got there. You would need to send supplies. We've talked about sending an in-situ resource utilization package, potentially, that could be either making fuel, making water. So all kinds of things that you can think that you would want to send to Mars before you sent humans. A cargo mission where you don't care that it might take 10, 11, 12 months to get there rather than 6 or 7 months, where you want to get humans there fast so you don't subject them to any more radiation than you have to. You don't care about that so much with cargo. So ion propulsion is this large ion propulsion stage is something that we really need tested for that. Then the final phase would be this exploration, where we would have crew out in cislunar space, working, living, doing a lot of things they would need to do in the Mars environment, having them do it in a place much closer to home in case something went wrong. So what's the timeline for all this? Right now, we have 2 things that we're developing to get ready for sending humans out beyond low Earth orbit. One of those is the development of a new launch vehicle called the SLS, because we love acronyms, or the Space Launch System. And the second is this Orion, which is the crew module and stage that is, of course, an international project. The Space Launch System is going to have its first test flight, I think, in 2018. I get these dates muddled all the time. Don't quote me on that. 2017. Okay, I thought it was either 17 or 18. The first flight of Orion is actually going to be not on the Space Launch System. It's actually going to be on a Delta rocket, and that will take place probably late this year. Then in 2017 again, okay, yeah, sorry, I should have gotten this right on the chart. EM1 is an uncrewed test where we will use now the Orion capsule, this time on top of the Space Launch System. And then we're moving towards a 2021 first crewed test, where we would probably just send the crew out, loop around the moon, bring them back, using the Orion SLS system. If the asteroid were ready, maybe we would start work at that point, but if not, then we would just bring the astronauts back again. In the meantime, in 2018, we would launch the asteroid retrieval mission, and again, try to have it back in the lunar vicinity by 2023 at the latest. We are using all these assets right now to finalize a target for selection, and we're also evaluating these 2 mission concepts, grabbing something small versus grabbing a boulder. Now again, one of the ways we chose this particular mission is, obviously, you have a limited budget envelope and you have a limited amount of time and you want to make progress. So what kind of a mission can you formulate that you can afford that moves you on this path to Mars? And that's how we came up with the Asteroid Redirect mission. And because of these various technologies that you can see on the slide that enables us to test, from extravehicular activity that the crew can be doing, that we need those capabilities, the solar electric propulsion that I talked about, in-space power and propulsion, things like very high efficiency solar arrays, to all kinds of things dealing with crew transportation and operations, testing things like crew food, crew health, all of these things we would be able to do in this set of missions. So we're really excited about finding a path forward that is affordable and allows us to exercise a lot of these capabilities in a way that we think we can achieve by the early 2020s. The President has put forward a goal of having humans in lunar orbit by the early 2030s, and this moves us on a path to achieve that. The idea is that by 2035, we would like to have the first humans down on the surface of Mars. Obviously, again, there's a lot of work to do with that, with the two really tall tent poles being the entry, descent, and landing challenge that we have, and in terms of human health, the radiation environment between the Earth and Mars being something that we need to do still some more work on. So we have work to do, but I think this is an achievable goal to actually have something down on the surface of Mars in that time frame. And it's an incredibly exciting time because, again, I have this notion that it's going to take humans on the surface of Mars to actually get the science that ultimately is one of our chief reasons for wanting to be able to go. So it's a really exciting time, and it's good to be moving forward on this, and I think we're going to be able to achieve a lot in the next several years. So thank you, and I'm happy to take questions.